Can you hear me? Okay. Good morning. So I have to apologize for one thing in advance, and that is that you've actually heard by now most of the stuff in this talk. So you may be slightly bored. That's the advantage of having collaborators that have already gone before me and have given very good talks. So I will be, but then maybe I'll be able to get through it faster, so you get to have your coffee break earlier. So maybe there is an advantage for you. I'm going to be talking about using EMRIs to probe bumpy black hole spacetimes, and this is based on work that was done together with Jonathan Gare, Chao Li, Hua Feng, and Jeffrey Lovelace. So just a brief outline of the talk. I will first discuss what exactly I mean by bumpy black holes and why they're interesting to us. I will discuss our particular approach to studying them. I will focus on the analysis of geodesics in a particular example of a bumpy spacetime, namely the Manko-Novikov time spacetime, and I will describe a little bit later exactly what that is. And I'll specifically discuss one interesting feature, namely the potential loss of the third integral of motion and resulting chaotic behavior. And then at the end, I'll briefly mention our future plans and some outstanding issues. So what exactly are bumpy black holes? Well, Kostas has just spoken about that. They are models for stationary axisymmetric spacetimes with anomalous, meaning non-Kerr, higher order multiple moments. So as you've heard many times by now, and I'm sure you knew already, for the Kerr metric, all higher order multiples are determined by the mass and the spin, but a bumpy black hole is simply a stationary axisymmetric compact object where we assume that higher order multiples are not given by mass and spin, and in particular we will focus on objects with an anomalous quadrupole moment, so the first, the lowest of the non-Kerr moments. Why they're interesting? Well, basically as models for testing whether the compact objects are indeed Kerr black holes. And Kostas and Jonathan have already mentioned the details of what these non-Kerr black holes may be, whether we can view this as a test of the cosmic censorship conjecture, or a search for exotic compact objects such as boson stars, or whether you want to think of this as a null hypothesis test of the O'Hare theorem. I won't get into the details of how you want to view this test. Let's just say that we are going to focus on testing whether or not the compact object is a Kerr black hole, and if not, how can we characterize a deviation from Kerrness. Of course, all of this is only relevant if we can actually see bumpiness, if we can actually see this by looking at gravitational waves, the difference between a Kerr black hole and this bumpy object. So the primary question we want to answer is, how accurately can we determine the amplitude of an anomalous quadrupole moment from gravitational wave emission? This question is most easily answered in the context of LISA by considering extreme mass ratio inspirals, EMRIs. You can think of sort of a twofold reason for that. One is a physical reason. EMRIs will spend a lot of time in the strong field regime, and so you get to probe the strong field regime quite exquisitely with EMRIs and obtain a lot of information about it. The other reason is sort of a data analysis reason. In EMRIs, there are fewer things obscuring the information about the field and the properties of the massive object. For example, the spin of the smaller object is not relevant in various effects due to the coupling of the spin of the smaller object to, say, the spin of the larger object are therefore not relevant. So it's just easier to extract information about the higher order multiples of the larger object than it would have been with, say, a comparable mass binary. So some previous results that have already been mentioned. So I'll just go through these very quickly. Ryan claimed that he could detect the quadrupole moment for LISA to an accuracy of about 1.5% in the mid-90s, but he relied on using nearly circular, nearly equatorial orbits. We know that one of the strongest influences of the quadrupole moment, for example, is in the precession of the orbital plane due to spin-orbit coupling, and so Ryan had, in the way that he considered had missed that effect, and so we expect that his result would be an underestimate. Kostas had just spoken about the confusion problem that he and Stas encountered when with their approach. In their paper, they discussed equatorial geodesics without in-spiral. Actually, in the talk that he has given today, he has mentioned that now they've included the effects of the in-spiral and have found that that helps relieve the confusion problem. Kurt Cutler and Leo Barak have found that for LISA, they can determine the quarter-pole moment to an accuracy of about 1 part in 10 to the 4, and they have included all of the 3 effects of the quarter-pole moment, namely the evolution of the periastron precession and orbital plane precession, as well as the effect of the quarter-pole moment on the in-spiral rate. However, they've done this in a somewhat ad hoc manner. We are also doing it in a kludged manner, so I'm not claiming by any means that our results are going to be better than theirs, but I think it may be worthwhile to conduct an additional check. And just as an aside, even though this is a meeting on LISA, it should be pointed out that there may be another way to see bumpiness, perhaps even earlier than LISA. With LIGO, advanced LIGO may be able to see intermediate mass ratio in-spirals into intermediate mass black holes, assuming that Cole is right and intermediate mass black holes exist. And if so, it may be possible to actually test, although probably not as precisely as with LISA, test the value of an anomalous quarter-pole moment. And a group of us are working on this, and there's a paper currently in preparation by Brown et al. So what is our program? So the program is, very briefly, first understand geodesics in bumpy spacetimes, then look at kludged waveforms from these geodesics, and then eventually to study the actual in-spirals, again, kludged in-spirals, of course, and in-spiral waveforms in bumpy spacetimes. We are currently roughly here, meaning that we're just beginning to look at the in-spirals, but during this, the rest of this talk, I will focus mainly on the first step, understanding geodesics in bumpy spacetimes. So why do we need bumpy spacetimes? Couldn't we just do a decomposition in multiple moments, write down the whole series of multiple moments? Well, the problem is that close to the black hole, and that's the regime where we want to test things, right, in the strong field regime, the higher order terms in this expansion don't, we would need to include too many higher order terms, essentially, to do this properly, because they fall off as high powers of 1 over r, and so close to the black hole, they may actually be significant. So therefore, we've tried to look for other models of bumpy spacetimes, and one that in particular we've settled on was proposed by Manko and Novikov in the mid-90s. It's, oh, I'm sorry, I'm in the way. It's an exact vacuum solution that is stationary and axisymmetric. It's obtained from the Ernst potential. I won't go into the details of how Manko and Novikov have computed it. But the key point is that it can be expressed in the form of wild metrics. So Manko and Novikov have specified what the 3 functions f, omega, and gamma are, and that completely specifies, of course, the metric. And particular values of f, omega, and gamma correspond exactly to the Kerr black hole. So the Kerr black hole is actually included as a special case. Other suggested bumpy spacetimes are the Collins and Hughes spacetime, which is actually obtained in a somewhat similar way, but it is a perturbative spacetime and does not include spin, so it's just a perturbation of Schwarzschild. Yunus and Gonzalez have suggested perturbing Kerr via the Chernovsky-Horry formalism from the Tucholsky function, and Lee and Lovelace have used a similar approach. And as Kostas recently described, he and Stas Babak have used the Hartle-Thorne approach to obtain a perturbative Kerr solution. We kind of like the idea of using an exact solution because we think that it allows us to probe the strong field regime more accurately and to look for such interesting effects as the loss of a third integral. So, yes? So the solution that we're using actually allows the specification of all higher order multiples, both mass and spin. The problem is that we cannot specify them individually, in the sense that I cannot just easily say, okay, I want a quarter pole moment that's different from Kerr, but all higher order multiples the same as Kerr. So really, when I say that we're using a different quarter pole moment than Kerr, we're also, the solution that we have also actually will have different higher order multiples as well, but we're just assuming that effect is not as significant. So the way that we compute geodesics is purely numerical. We just directly code up the second order geodesic equation. One key point is that unlike a lot of people who study this, we do not explicitly assume the conservation of energy and angular momentum. Energy and angular momentum are, of course, expected to be conserved because this is, after all, a stationary axisymmetric spacetime. But we choose not to explicitly put that conservation into the code precisely so that we can actually check the accuracy of our computations by by seeing whether energy, angular momentum, and the norm of the fore velocity, or the mass, if you wish, are in fact conserved. So how do we look for evidence of the existence of a third integral, right? Remember that in Kerr there is in addition to energy and angular momentum, there is a Carter constant, a third integral, and the question is, does that persist in this non-Kerr spacetime, in this bumpy spacetime? So the way that we look for the existence of a third integral is using the Poincare map technique. We basically pick a particular plane at constant z. I'm using roughly cylindrical coordinates. Rho and z are actually slightly different than the standard cylindrical coordinates, but just for simplicity, assume that that's what they are. So I pick a constant z plane. I look at different orbital crossings of it, and at each orbital crossing, I plot rho dot versus rho, right? So I plot the radial velocity versus the radius, and the idea is that if I obtain a closed curve as a result of this plot, then I have a third integral, right? Because just in the same way that, for example, if energy and angular momentum are conserved, then t dot and phi dot are just functions of rho and z, then if for every z equals constant plane, I find that rho dot is a function of rho, perhaps a multivariate function of rho, but a closed curve nonetheless, and then z dot would also be a function of rho and z simply from the conservation of the fore velocity, that would mean that I have found my third integral. And so we look for the disappearance of the third integral of motion. Now, just to give you an example of a Poincare map, this is actually not GR. This is just a Newtonian potential with a hexadecapole moment that Chao mentioned in his talk yesterday. And what is plotted on the left and on the right here are both Poincare maps. So rho dot is on the y-axis, rho is on the x-axis. The only difference is the initial conditions. Here, the radius varies from about 12 m to about 13 m, and here it's much closer in, about 7 to 8 m. And you see that whereas in the plot on the left, there is a very clear closed curve, meaning that there is the motion looks completely regular, right? And you might believe that there is a third integral. On the right, we see that in this regime where the effect of the higher order multiple is stronger, there is a clear loss of a third integral of motion. The Poincare map looks entirely chaotic. Before I show you the Poincare maps for the Canonical spacetime, let me describe one interesting feature, and that is the fact that there are two allowed regions for orbits in the Canonical spacetime for particular values of energy and angular momentum. So what I mean by allowed regions for orbits, well, I can write down this effective potential, which is a function of rho z, energy and angular momentum, which is just equal to rho dot squared plus z dot squared. This quantity obviously has to be positive, and so the effective potential must be positive, so I can think of the curves where the effective potential is 0 as boundaries of allowed regions. So this is a plot for just Schwarzschild. I just picked some value of energy and angular momentum, and we see, okay, so here is this is a plot of, on here I have Z and here I have rho, and so this is essentially where my particle is allowed to be in the Schwarzschild spacetime. If the particle has this value of energy and angular momentum, so there is some set region where it's allowed to be. This region right here, it just corresponds to orbits that are just about to plunge in, so they're not interesting. This is connected to the horizon, which is at rho equals 0 in these coordinates. Now I look at Kerr, so I put in a spin. I've somewhat deformed this region, but otherwise things look basically the same. And now I'm going to put in a non-Kerr quarter-pole moment, additional quarter-pole moment, and things look very odd. So right here, I have formed a new region, which I'm going to call the inner bound region. So this stuff over here that looks really funny, those are still plunging orbits. Those are connected to the singularity. But this region right here actually is not connected directly to the singularity or to the horizon. And this is an inner region, and this is an outer region. And as you will see in a moment, the geodesics looks very different in the inner and outer region. So in the outer region, and this is just some particular value of initial conditions chosen in the outer region, but this is more or less typical for any initial conditions I might pick in the outer region, I find a Poincare map that shows seemingly completely regular motion. Right? Again, rho dot versus rho is being plotted. This is a closed curve, regular motion, everybody's happy. But now I go into the inner region, pick the initial conditions in the inner region, and I find the following Poincare map. This clearly shows evidence of chaos. So what's going on here? Well, so one thing to realize is that since I have found at least one set of initial conditions that leads to chaos, that means that the motion is chaotic. All motion is chaotic. Remember that chaos is not a function of initial conditions, it's a function of the equations of motion, right? Either your equations of motions are chaotic or they're not. And if for some initial conditions you find chaos, that basically means that there is no there's no full set of analytic integrals, right? You're not, you don't have the full set of isolating integrals that restrict you to a particular track in phase space. And so in general, the motion is indeed chaotic. However, as the KM theorem, the Kolmogorov-Arnold-Moser theorem that Qiao had mentioned yesterday points out, it is possible to have some initial conditions for which a near invariant exists. So the KM theorem roughly says the following, that if you start out with integrable equations of motion and then you perturb them in such a way that you begin to see evidence of chaos, you will still have some invariant tori such that if your initial conditions are close enough to these invariant tori, then you essentially stay on orbits where the dynamics look almost regular. Now, the one thing that's a little bit unusual about this particular spacetime, the canonical spacetime, is this very clear separation between regions of regular motion or seemingly regular motion and regions of obviously chaotic motion. More typically, you might see something like this. This is also a plot that was produced with the same program but using a slightly different spacetime, the Guérin-Letellier spacetime. And in this Guérin-Letellier spacetime, this is again a Poincare map. Here, the different colors correspond to different choices of initial conditions. And as you can see, we sort of have interspersed regions of regular motion and chaotic motion. So, for example, here the motion looks very regular, or over here the Poincare map looks regular. Here it's chaotic. So this is more typical. What we find is something that's fairly unusual. This distinct separation of a region where all of the initial conditions seem to be regular versus a region where all initial conditions seem to lead to strongly chaotic motion. And possibly the conjecture is that maybe the KM theorem doesn't strictly apply to our case because we don't have really a weak perturbation. We have this rather strong qualitative difference between having even a small quarter-pole moment and none at all. Namely, when we put in even a small quarter-pole moment, we no longer have a horizon, we have a naked singularity. So there is a qualitative difference from a Kerr black hole. So maybe that's, since we're exploring, especially with these strongly chaotic orbits, we're exploring the region very close to the, yes? Well, we would have a naked singularity. I mean, by the no-Harris theorem, right? We would have a naked singularity for any value of the quarter pole moment that we would pick, right? Right. So okay. So one interesting question, of course, is do we really need to worry about the inner region, right? Is it actually accessible in the course of an in-spiral? And without boring you about the details, since time is running low, let me just say that indications are that during the actual course of an in-spiral, because of the way that energy and angular momentum are lost during the in-spiral, we do not expect that the particle will ever actually end up in this inner region. And so it's mathematically amusing, but it's probably not astrophysically relevant. The other question is, well, what about the outer region? Because we've just said that even in the outer region, even though orbits look regular, really the equations are still chaotic. Does that mean that it will create difficulties for us when we try to do analysis? And the answer is probably not. And the reason is that really we have we're very close to having an invariant, an effective additional integral in the outer region. Here I'm actually plotting z versus rho, and you can see this very regular pattern of motion. I'm plotting this just along the entire geodesic in the outer region. This very regular pattern motion with these kinds of crossings suggests that we're very likely to have an invariant which is second order or fourth order in the velocities. Even more importantly is the frequency decomposition of rho and z motion. Here I'm showing on the x-axis is time, on the y-axis is just some arbitrarily scaled Fourier transform. But notice that there are very distinct peaks when I do the frequency decomposition of the rho and z motion. Blue is rho, green is z on this plot. That means that really we have both in rho and z motion to an accuracy of something like a part in 10 to the fifth. We have we check the first 20 frequency peaks, and we find that they are all harmonics of two fundamental frequencies, which means that Chow's description yesterday of trying to extend Ryan's theorem to these more generic spacetimes by still considering the fact that essentially we have two, or rather three, once you include phi motion, distinct frequencies, distinct fundamental frequencies, is still applicable. Another way to characterize geodesics is by looking at precession rates. Precession rates meaning both periapsis precession and orbital plane precession. The difficulty here is when you're making the comparison, exactly how do you identify two orbits in two different spacetimes, right? I mean, you could try to identify them, for example, by saying that you're looking at orbits with the same radius, but actually that turns out to be a bad idea because different spacetimes have different meanings of the radial coordinate, and other ways perhaps to look at orbits with the same energy and angular momentum. Turns out actually the best way is to identify orbits with the same azimuthal frequency. Well, the reason is rather obvious, that really what you care about are orbits with similar waveforms, and the azimuthal frequency provides the primary imprint on the waveform. Okay, and so very briefly, I've mentioned that we need to look at the kludged waveforms, and then eventually, of course, the interesting thing will be to look at kludged in-spirals, because this will really allow us to put quantitative limits on how large of a quarter pole moment we can extract. There are problems here, namely how exactly do we write down the self-force? How do we put an acceleration term into those geodesic equations? And this is something that we are still trying to figure out, at least. Obviously, we are not going to get this correctly, but at least how to pick a reasonable kludged way of doing that. So in summary, the LISA EMRIs are high-quality probes of strong gravity environments near massive black hole horizons. And so, in principle at least, an accurate extraction of an anomalous quarter pole moment should be possible because of its effect on the periapsis precession, orbital plane precession due to the spin-orbit coupling and the in-spiral rate. Chaotic motion is mathematically possible in bumpy spacetimes, but it's probably not astrophysically relevant, and we still need further study to get limits on how well Q can be extracted, as well as practical methods for detecting and analyzing bumpy EMRIs. Thank you.
One other question about a possible chaotic link. If the secondary body is spinning, does any interaction with an anomalous quadrupole moment lead to additional complexities and possible chaos in that sense? I mean, maybe you haven't studied that, but do you have any thoughts on it?
So I would imagine that the answer is yes, that it could introduce additional complexities. We have, at this point, as I said, we've restricted ourselves to looking at point particles moving on geodesics, and even the next step, we're still planning to just assume that the smaller object is we're planning to include radiation reaction, but in an inclusive way, and we're still planning to say that the smaller object is essentially, in the adiabatic approximation, moving on geodesics and moving between them due to radiation reaction, but without including the spin of the smaller object. I suppose the hope is that, at least for EMRIs, the spin of the smaller object is not going to be a strong factor.
The result is that you have chaotic behavior if the spin is unnaturally large, irrelevant for the real systems. So for all practical purposes, there is no chaos induced by the spin of the small particle, of the point particle.
Right, I remember that result.
Yeah, that's for care.
Yeah,
Nobody has done it. So.
So we were looking at one class of these Manco solutions with the idea of reproducing the exterior space-time of a rotating neutron star, reproducing the first few multiple moments. And what we found in that case is that there was only a limited set of the parameter space in the Manco solution that made sense as you reduce the spin to 0. So not all allowed values of the quadruple moment were actually making sense if you wanted to reproduce an object that looks similar to a neutron star. I would guess, of course, the interest in your case is different because you're exploring orbits for a generic space-time, but perhaps it would make sense to restrict the space of allowed extra multiple moments to make it look more like a deformed curved black hole and avoid, singular behaviors or stuff. Maybe we can talk about it later.
Right. So I agree that I mean I think really one of the results that we would like to get out of this is to say, well, how large would an anomalous quadrupole moment have to be in order to be detectable, right? I realize that we're not trying to make the claim that any actual object in the universe is really going to be a Manko-Novikov type singularity. We're just using this as a straw man, as a model for something with a non-Kerr quadrupole moment, and just trying to get a limit on how large a quadrupole moment has to be detectable, and also how we should go about detecting it, right? Because possibly if the quadrupole moment is significant enough, then maybe just even for the purpose of detection, we would need to have some other waveforms. Maybe it won't be detectable with standard. It won't match the standard Kerr EMRI waveforms well enough to be detectable, but that's less likely. I suspect that probably it won't differ so much as to not be detectable, but more important is how do you practically go about extracting the information once you have made a detection, extracting the information about higher order multiples. And so this is just a model for that.
Last comment or question, Jonathan?
I was just going to say that we do, I mean, if we set this small parameter to 0, we reproduce Kerr precisely. So, I mean, you were saying that you had this strange limit for your, in the case you were considering. So, yes, when the small parameter doesn't just change the quadrupole moment, it changes the higher moments. But by tuning it to 0, you do reproduce Kerr precisely. So in a sense, it's a test of how big a deviation within this class of Canonical solutions we could see.
Right. So this is the Q parameter that Jonathan was talking about. Sorry, I'm shining it as myself. So this is the Q parameter that Jonathan was talking about. I've picked some rather large values for it for the purpose of this talk, just to exaggerate some of the effects to make them more visible for you. But that's all. Right. In fact, if you set A to be 0 and Q to be non-zero, you actually get an exact vacuum solution version of what Collins and Hughes had done, where they had done a perturbed Schwarzschild with a perturbative quarter-pole moment. And in fact, by looking at things such as periapsis precession rates, we found that for at least further away from the black hole, for choosing the same value of Q as Collins and Hughes had done, we actually match their results.
Okay, I suggest we break here for coffee. One small announcement: if you need a taxi for today to the airport, please talk to Pau now, right? And we should reconvene here at 5 to